Okay, today we're going to look at a 3D curved space and a little general relativity. Here's the general relativity that I promised you on my other curved space lecture. So you might want to watch. I have a two-dimensional curved space lecture also if you want to go look at that video. Okay, so let's take a look at a three-dimensional curved space. Unfortunately, for three-dimensional, we won't be able to draw the pictures that we did with two-dimensional. It's a little bit more abstract. But we can generalize our rules on the two-dimensional curved space if you want to go back and watch that one before you watch this one. You will understand. You might understand this better unless you're a very seasoned curved space person. Okay, so what we're going to do is, in three-dimensional curved space, instead of drawing it, a two-dimensional object, we will draw a three-dimensional object like a sphere. And what we'll do is we'll measure the radius of the sphere and then measure the area of the sphere. Okay. Once you measure the radius of the sphere and the radius of the sphere, and the area of the sphere, you'll notice that normally the radius would equal the square root of the area divided by 4 pi. But what you'll find if you're in a positively curved space is that the radius of the sphere will be greater than the square root of the area divided by 4 pi. If you're in negatively curved space, you'll find that the radius measured, when you measure the radius and you measure the area of the surface inside your space, it will be less than the square root of the area measured divided by 4 pi. We'll talk a little bit about Einstein's general relativity, not too much, but what you have is you have a spherical area, and it's surrounding some mass inside this area. You have let's say a mean radius, because sometimes you can't get only one radius when you have a bunch of stars or a galaxy or whatever. So we'll do a mean radius of the area. And what Einstein said was that if you take your measured mean radius minus the square root of the area of the area that you're talking about, the volume that you're talking about, divided by the 4 pi, the square root of the area of the region in space, divided by 4 pi, it will equal g, which is 6.67 times 10 to the minus 11, the gravitational constant, times the mass that's inside the area that you're measuring, and divided by 3, and the speed of light squared. And then I wrote here the mass will equal 4 pi times the density times the radius measured cubed divided by 3 if you can't measure the mass for some reason and can only measure the density, which you assume is somewhat homogeneous inside your spherical area. All right. Well, I hope you enjoyed this lecture, and I look forward to any comments at the bottom. Thank you very much.